light. In this lesson, we're talking about what is light, the properties of light, luminous and non-luminous objects, the history of light, the electromagnetic spectrum, prisms, and then color and color blindness. So where does light come from? Well, it all comes from the sun. It provides energy in the form of light through a process called nuclear fusion. And nuclear fusion occurs when two atoms that naturally repel each other are pulled together by a superior force and the atoms fuse together. Nuclear fusion produces energy that reaches us as heat and light. The sun provides the energy that enables life on Earth. Without it, we wouldn't be able to survive, nor would anything else. Properties of light. Number one, light travels in straight lines. Now you can see this very easily when you're talking about lasers, but you can also see it when you're doing shadows on the wall, right? If you block light, the light is blocked in a certain way, and it stays that way all the way to where it strikes the wall or whatever surface it's reflecting off of. Lasers, if you point a laser and it's a really focused laser, you can actually get a really nice beam, as you can see here on this red line. You can also see it pretty well with this laser show in the bottom corner, as with the laser eyes coming from the robot. But either way, all these lines are straight. They might spread out, they might get further away as they move away from the source, so instead of being perfectly straight parallel lines, they might diverge a little bit. But the key thing is, these lines are going to be straight. Number two, light travels very, very fast. In fact, it moves so fast that it could go around the Earth 7.5 times in 1 second. It travels at about 300,000 kilometers per second, or 3.0 times 10 to the 8 meters per second. Really, really fast. Now, one of the phenomena about light is that it travels way faster than sound. So when you hear thunder and lightning, the thunder is actually caused by the lightning. So as the lightning goes through the air, it pushes the air molecules out of the way really, really fast. So things like oxygen, nitrogen get shoved out of the way really, really quickly as the air heats up. The air heats up because of the lightning. As they move out of the way, they create that boom that we hear as thunder. And a good way to actually see this as well and hear this is if you go to a baseball game and you're sitting really far away, because it's kind of neat. You'll see the batter hit the ball, and then you'll hear the crack of the bat, but it'll be like half a second to a full second later. It's pretty amazing. Now, how fast does sound travel? We just talked, first of all, that light travels at 3.0 times 10 to the 8 meters per second, whereas sound is going to travel at 340 meters per second. So a huge difference. Number three, we see things because they reflect light into our eyes. Unless you are a luminous object like the sun, you're not going to be seen if there's no light to be reflected off of you. So for instance, a book can't be seen in the pitch black. You need some kind of light source like the sun or a lamp to shine on the book, and then that book reflects the light into your eyes so that you can actually see it. And this brings us to our luminous and non-luminous. Now, I said everything needs to have light reflected off of it unless it's luminous. Well, the thing like the sun, lights, TV, your phone, these are all luminous objects, at least the screen part is. It's giving off light. You can see it when there's no other light around. But a non-luminous object, like the moon, like people, like books, they need to have a light source shining on them for you to see them. 4. Shadows are places where light is blocked. Now, if you stand between the sun and pavement, for instance, the sun is going to shine on you, and you are going to block those rays of sun in exactly your shape, and that's how we get a shadow on the ground. So to summarize, number 1, light travels in straight lines. Number 2, light travels much, much faster than sound. Number 3, we see things because they reflect light into our eyes. And number 4, shadows are formed when light is blocked by an object. History. So unlike heat and sound energy, which requires a medium, a physical substance like air or water to move through, light does not, which is really good because light needs to travel through empty space. And if it needed a medium to travel through, it wouldn't be able to go from the sun to Earth. Light is instead transferred through a process called radiation at a speed of 3.0 times 10 to the 8 meters per second. Light is also classified as an electromagnetic wave. So what is an electromagnetic wave? Well, we've identified many types of electromagnetic waves which make up the electromagnetic spectrum. Light makes up this tiny little sliver right there. Bigger parts of the electromagnetic spectrum include things like infrared light, radio waves, ultraviolet, X-rays, gamma rays. But as I said, visible light only makes up a really small section of this spectrum. And then we could divide the visible spectrum into its wavelengths from red all the way down to a violet blue color. Now, as we decrease the wavelength, so you can see this is 700 nanometers, this is 400, so wavelength is lower here. So we say wavelength is represented by that symbol called lambda. So you say that lambda is bigger on the left, smaller on the right. So as we decrease wavelength, we increase frequency and energy. So gamma rays have a higher frequency, right? Frequency goes up down here, and frequency is lower down here. If it has a higher frequency, it's going to have more energy. and it's going to be more dangerous. So if you get struck by gamma rays, you're going to be in a lot more trouble than if you're struck by radio waves, which we're struck by all the time. Prisms and rainbows. Using the simulation, analyze the effects of a prism on white light and describe why this occurs. You use this information to explain why a rainbow occurs. So I want you to pause the video, I want you to click the simulation, and I want you to play around with it a little bit, and then I want you to answer the question, why a rainbow occurs. Colors and rainbows. White light is not a single color, it's made up of a mixture of the 7 colors. We can demonstrate this by splitting white light with a prism, which you just did using the simulation. And this is how rainbows are formed. Sunlight is split up by the raindrops. So you have your sun out here, and it's coming in as its regular white light. And you have a raindrop here, which is going to act as our prism. So you have our light coming in, and as it hits that raindrop, it's going to break that light into its different components. So everything from blue up into red is going to be split apart, and we're going to get a rainbow as a result. Now, how do you remember the colors of the rainbow? Well, we have Roy G. Biv. Roy, R-O-Y, so that's Roy. Right? Roy. And then G, Biv. B-I-V. Roy G. Biv. Now I want you to pause the video again. I want you to check out this simulation. And I want you to see what happens when you put 2 prisms next to each other. Split the light in the first one, and then try to put it back together in the second one. See what happens. And that brings us back to our adding colors. So white light can be split up to make the 7 colors, but then we can also put these colors back again. Now the primary colors of light are red, blue, and green, which is different from the primary paint color, so keep that in mind. Now we can add our different light colors to make every different color, including white, which you can see here, that if we add everything back together like we do with the second prism, we actually end up again with white. But if you add different shades of color, for instance, if you put red and green together, then you get yellow. If you put green and blue together, you get this cyan color, and so on. And that's actually how we see. So we see different colors based on the mixture of light that enters our eyes. So if you are looking at an object and that object is reflecting some red and green light, you're going to see it as a yellow. If it's reflecting something that's more red and less green, then you see something closer to red. And this is well seen using the simulation here. So again, I want you to pause the video, check out this simulation, and see what the different colors look like when you add different amounts. Seeing color. The color an object appears depends on the color of light it reflects, and that's what I was just talking about. So for example, a red book is only going to reflect red light. It's going to absorb all the other colors. So everything here from the orange down to the indigo is actually absorbed by the book, and eventually that book would get a little bit warmer if you shone light on it. A pair of blue pants would reflect only blue light. All the other colors, so these guys here, pretty much, would be absorbed by the pants, and probably that would be absorbed by the pants as well, because it looks like the pants are giving off just more of this light blue color. So you might get a tiny bit of this guy absorbed, but probably some of that would be reflected as well. Now a white hat would reflect all the 7 colors, because white is made up of all of the colors put together. So if you want to stay cool in the summer, wear something that's white, because white is going to reflect all the different colors, whereas something like black is going to absorb all the different colors and make you warmer. Now if we look at a colored object in colored light, we can see something very different. So for example, if you consider a soccer uniform, our shirt looks red because it reflects the red light, and our shorts look blue because it reflects the blue light. But what if we take some of those colors away? So if we only shone red light at this red-blue combination, the red shirt would still reflect the red because red is available. But since there's no blue available, there's nothing to reflect, so our blue pants actually look black. And then likewise, if we only shone blue light, the blue pants would still reflect the blue, so that's fine. But the red shirt would have nothing to reflect, and therefore it would appear black. And we can use filters to show this as well. So filters can be used to block out different colors of light, and that's often how we make different light bulb colors. Like if you look at Christmas light colors, it's generally just a filter. So if you put a red filter on a light bulb, that red filter is going to absorb all the colors except red. It's going to let red pass through. If you put a magenta filter on a light bulb, it's going to absorb everything here and that, and it's going to let through the purple, blue, and red, and it's going to make our magenta color. So we can use these different color filters to make any array of lights that we like. Color blindness. The tricky thing about color blindness is that many people don't know they're colorblind until they get tested. In fact, 40% of colorblind pupils currently leaving secondary school are unaware that they're colorblind. And I have a quick story about this. So when I was getting my eyes checked for laser eye surgery, I was talking to the optometrist, and he was telling me that he was examining someone who was going to be a police officer, And one of the tests that a police officer needs to be able to pass is be able to see color. And the police officer unfortunately failed the test because he was colorblind. And as a result, he wasn't actually able to be an active, on-duty police officer because he was colorblind. But he didn't know, because you only know what you know. And if you're never tested, if you're never actually shown these different colors and these different combinations, you're never really going to know, because you grow up seeing a certain thing a certain way and you just think that that's right. So let's try this. Now, this is by no means a medically approved test, but it is a test that looks at the different color combinations. And you can see what it does is that it puts these animals as different colors compared to similar colors. So if you are red-green colorblind, you might have trouble seeing the bear compared to the green surrounding, because this reddy-orange color will look very similar to the green color around it. It would kind of just look like gray, and you wouldn't see the difference. So I want you to pause the video, and I want you to count as many animals as you can. So did you get all 6? Sometimes you might miss 1 or 2 that you couldn't quite see. Once you take a look at the circled ones, you should be able to see the difference between the animal and the colors surrounding them. So what causes red-green color blindness, or color blindness in general? Well, red-green color blindness is caused by a gene on the X chromosome. Therefore, since males have one X and one Y, while females carry 2 X's, this issue is predominantly found in males. Because what happens is that if the female has a good X and an X that is colorblind, this good X will overcome the bad X, and they'll still be able to see color. But if a male has a colorblind X, and of course the Y that goes with it, then he will not be able to see color, because there's nothing to compensate for that X. Now, for a female to be colorblind, she needs to have a father who is colorblind and a mother who at least is what's called a carrier. This person is a carrier of the colorblind. It's a carrier of it. So in this case, the mother would give either this X here or this X here. So how common is this? Well, it's pretty common among males. It's actually 7 to 10% of the population, which is pretty amazing. If you have 100 people, then you're going to have 7 to 10 of those people, if you choose them randomly, of course, that are colorblind if you're a male. Whereas females, it's pretty close to, not 0, but it's a very low percentage, because as I said, you need to have a father who is colorblind and a mother who at least is a carrier, which is going to be much more rare than just having a mother who is a carrier of colorblindness. Blue color blindness. Blue color blindness is equally unlikely for both males and females, as the deficit gene is found on chromosome 7. These people can't see blue color light. So in both of these cases, the problem isn't as straightforward as not seeing blue, red, or green light. It's always going to be a version of this. You're not going to be completely colorblind, probably not going to be completely colorblind when you can't see any red or any green light. You just might not be able to see red or green light well, or blue light well. So some of the colors that you should be seeing, you don't quite see, but again, you don't really notice it because it's what you grew up looking at. And unless you're tested, you don't really see the difference anyways. And that concludes our lesson on light.